All right, so here's a fourth example of this full vector motion. So you throw an apple at a 45-degree angle to the horizontal, aiming at a friend who's sitting in a tree a distance h above level ground. At the instant you throw your apple, your friend drops another apple. Part A, show that the two apples will collide no matter what your apple's initial speed, provided it's greater than some minimum value. And part B, find an expression for that minimum speed. So first thing we want to do here is just get a little bit of a visual as to what's going on. So we have our axis here, and it says that our friend is sitting some distance away on level ground. So we can just draw this exactly. There's no slopes or anything. It's just perfectly flat. And it says he's sitting a distance h above level ground. And we fire or throw our apple at a 45-degree angle. So I'm going to go ahead and get a velocity vector here at a 45-degree angle. This is the initial velocity vector of our apple, and this is 45 degrees. All right, and it says our friend is sitting some distance away h, and so maybe he's sitting, let's say, maybe right here. And so the distance that he's sitting away is h. So if we draw this just as a reference, right here is h distance away in the horizontal. And we won't draw the tree or anything, but basically you throw a ball that has some path like this, or an apple rather, and then he drops one that has some path like this. And what we're trying to show is that they will collide no matter how fast you throw your apple. All right, so this problem involves kind of realizing what exactly is going on with the distance away here. If we have a 45-degree angle from the horizontal, that also means our vertical angle right here is 45 degrees. So before we go any further, I encourage you to maybe pause and try to figure out how to prove this. All right, so we know that the angle from the vertical is also 45 degrees. And if he's sitting exactly 45 degrees from us, then we know that this height right here is also h. And that's going to be a key piece to solving this problem. He's a perfect distance h in the horizontal and the vertical due to the fact that he's sitting 45 degrees away from us, or we throw this apple 45 degrees to the horizontal toward him. All right, now one other thing that is always useful in these kinematic problems that involve collisions, we want to make a note. It's this note, whenever we're talking about a collision, mathematically a good way to approach this is the same position x and y at the same time t. So looking at this situation that we have here, we know that if these two objects are to collide, then the horizontal position of our apple has to at some point be h, because the horizontal position of this apple that your friend dropped is not changing. He dropped it straight down. And so the position of our thrown apple has to be h if it's going to collide. So let's figure out what time or when our thrown apple is going to hit that horizontal distance h. So before we even start the math, I just want to get down information. So apple 1, our thrown apple, as always, if we're throwing something, we always want to draw our coordinate system to start at the origin. Now, if we're interested in the time t, we won't end up using the trajectory equation. That doesn't involve t, but it's always just useful anyway. Because if we were using that trajectory equation, we would have to start at the origin. So we've drawn this one at the origin anyway. So our initial position in the x is 0, and our initial position in the y was 0. What about our initial velocity in the x? Our initial velocity, it should be initial velocity in the x direction, Well, it's going to be the component of our initial velocity in that direction, and this is going to be the magnitude of the initial velocity times cosine of our launch angle. And similarly, for y, it's going to be the magnitude, our initial velocity in the y direction will be the magnitude of the full initial velocity vector times the sine of our launch angle. Now, for acceleration, we just threw the apple and then released it. So in the x direction, we have no acceleration, 0 meters per second squared. In the y direction, after we released it, gravity is acting on our object. So the acceleration in the y direction is g. And let me slide all of this over just a tad. And so we have some information, quite a bit of information about apple 1. Now let's get some information about apple 2, our friend's apple that he dropped. Well, his initial position in the x direction, we were given as h, and then since he's sitting 45 degrees away from us, by symmetry of the vertical and horizontal split by the angle 45 degrees, we know that he's also at a position h above us. All right? Now, his initial velocity in the x direction, the problem says that he dropped an apple up here. So if he dropped it, his initial velocity was 0. Like right when he releases the apple, it's moving at 0 meters per second. So for both the x and the y direction, the initial velocity was 0 meters per second. Now, similarly, we're not accelerating apple number 2 in either direction, so that's just going to be 0 meters per second squared. And similarly, again, the acceleration in the y direction is going to be g. Okay, so we've got a bunch of information, and we can make one final note over here that our launch angle was 45 degrees. And so now we're ready to start solving. We said that we want to know the time when the first apple reaches the horizontal position of the second apple. So let's look at the position in the horizontal for apple 1. Well, our kinematic for that is our final position equals our initial position plus initial velocity in the x times t plus the acceleration in the x times t squared over 2. But we can make some cancellations. Our acceleration in the x was 0, so that whole term goes away. And our initial position in the x, we started at the origin, so that's going to be 0. And so we have those two terms cancel out, and now we have the expression x equals v naught x times t. So if we solve for t here, we get t equals x over v naught x. And then we can substitute our known values. We want to know this final position. We want to know the time when apple 1 is at the horizontal position h, same as apple 2. And we said the initial velocity in the x direction, which we have written down up here, is just going to be the magnitude of the initial velocity times cosine of our launch angle. So now we have this time t, and we know that this crosses, our first apple crosses the horizontal position h at this particular time. So let's figure out where it is in the vertical at this time. Well, our vertical position for apple number 1 is going to be y equals y naught plus v naught in the y direction times t, and then it's going to be plus ay t squared over 2. So let's plug in some of these values. We know our first apple started at 0, so our initial position here is 0, so we don't have to worry about that. And so now let's substitute in our t value. So at this particular time, our position in the vertical is y equals, now the initial velocity in the y direction was just the magnitude of the entire initial velocity times sine of our launch angle theta. And then t, we're going to plug in this t, was v naught cosine of our launch angle in the denominator divided by h in the numerator. Now, this acceleration in the y direction, that's gravity, and it's accelerating downward. So this is going to be minus g over 2. And then t squared, well, that's v naught cosine theta over or under h squared. So let's simplify this a little bit. We have that this v naught and this v naught cancel, and then sine theta over cosine theta. Our launch angle up here is 45 degrees. Sine of 45 degrees and cosine of 45 degrees are the same thing. They're both root 2 over 2. So sine over cosine of 45 degrees, which is also tangent of 45 degrees, is just 1. So these just become 1. They cancel out as well. And so what we have left is y equals, on this side we just have h, and then over here we have minus gh squared over 2v naught squared cosine squared of our launch angle theta. So that's the vertical position of apple number 1. And now we want to check at this particular time, what is the vertical position of apple number 2? If we're trying to confirm that they collide, we need to confirm that these vertical positions are the same. So let's get the same equation down for apple number 2. Y equals y naught plus v naught yt plus ayt squared over 2. Now, what was the initial position of apple number 2? It was h. We said that apple number 2 started up here at h. So we can substitute that in. So y equals h. But what about this initial velocity in the y direction? Apple number 2 was dropped. So it does not have any initial velocity in the y direction. That's just going to be 0. So that cancels out. And then what we're left with is plus ay over 2, but it's acceleration due to gravity. So this is minus g over 2. And then our t squared was v naught cosine theta over h squared. And what does that give us? That gives us that y equals h minus, and then we square that side, and we get gh squared over 2 v naught squared cosine squared of theta, our launch angle. And look, these two vertical positions are the same. So we had one time over here, we had one particular time, and we know that the horizontal positions were the same because apple number 2's horizontal position is not changing, and we calculated when apple number 1's horizontal position would be at the same horizontal as apple number 2. And then we took that time to find apple number 1's vertical position, and it lines up perfectly with apple number 2's vertical position. So at this particular time, they will collide. And notice we could put any initial velocity in here we want, and it will still collide. They will still hit in midair. So that's part A. We've shown that they will collide, but it says they will only collide provided the initial velocity is greater than some minimum value. And so let's kind of think about that. What could that possibly be? Well, we know if we threw our apple at a very light speed, maybe it doesn't even reach this position. Maybe we just throw it and it just kind of lands here. So we have to at least throw it far enough to cover the distance h between where we started and the horizontal position of our friend. And the problem said that we were on level ground, so we can use the horizontal range on level ground equation because we just want it to be far enough to land the same height, but where we started at. We want to at least throw it that far. So let's use our level ground equation. The range is going to be x equals v naught squared over g times sine of 2 times theta. And we want to know the speed v that will give us the range h. And this should actually be for apple 1. We want to throw apple 1 at least that far. So I'll change that to brown just to keep consistent with our colors so far. So we want the range to at least be h, so that'll be our x. And then we get v naught squared over g. But what about this sine 2 theta? Well, our theta was 45 degrees. 2 times 45 degrees is 90, and sine of 90 is just 1. So we just have this expression here. And so if we solve For the initial velocity, we can multiply both sides by g and then take the square root. And so our initial velocity is root g times h, and that is the minimum speed at which we must throw apple 1 for it to reach the horizontal position h and collide with apple number 2.